Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is bilinear method of IIR filter design. A common method of creating digital IIR filters is to transform a continuous time filter that we have designed into a discrete time filter. This is commonly performed by a transformation called bilinear transformation, also known as Tuston's method. Given a stable and causal analog filter, the bilinear transformation returns a stable and causal digital filter while preserving the order of the filter. The bilinear transformation maps the S-plane into the Z-plane according to the formula shown here. Here T is the sampling period. Consider the unit circle e to the power minus j omega in the Z-plane and apply the bilinear transformation to the unit circle. It will map it to the imaginary axis as shown here. Here we are using capital omega and omega to denote analog frequencies and digital frequencies respectively. So we have a nonlinear mapping between the analog and digital frequencies. If we rewrite the transformation as shown here and use the Euler formula and simplify further, we get the reverse mapping as shown here. You can see this transformation, which is called a pre-warping transformation, in the plot shown here. Also, the left half S-plane is mapped to the interior of the unit circle on the Z-plane as you see here. This means that the stable systems in one domain map into stable systems in the other domain. Again, the imaginary axis S equal to j omega maps to the unit circle e to the power j omega. If we take frequencies uniformly distributed on the imaginary axis in the S-plane, the plot here shows how they are mapped onto the unit circle in the Z-plane. Given the transfer function of an analog filter as shown here, let's find the transfer function of the corresponding discrete time filter using the bilinear transformation, assuming that the sampling period is 1. Using the Wolfram language, we can apply the bilinear transformation and get the transfer function of the discrete time filter. As shown here, the bilinear transformation preserves the order of the filter. We could also use the function to discrete time model to perform the transformation and get the same result. Here you can see the frequency responses of the two filters, the analog filter and the discrete time filter. In the previous example, we had the transfer function of an analog filter. We applied the bilinear transformation and obtained the corresponding discrete time filter. Now for our design problem, starting with a desired magnitude response specification for the digital filter, we first transform the specification using the pre-warping transformation, as shown here, design the equivalent analog filter, and then use bilinear transformation to map the analog filter to the desired digital filter. Let's look at an example. Let's obtain a second-order IIR low-pass Butterworth filter with cutoff frequency equal to pi over 3. As we mentioned previously, first we pre-warp the discrete time frequency using the bilinear transformation to obtain the corresponding analog frequency. Then we compute the analog Butterworth transfer function given the cutoff frequency and the order of the filter. We can plot the magnitude response of the low-pass filter to see how it changes over frequency. Now that we have the analog design, we use the bilinear transformation to obtain the transfer function of the digital filter, or use a function to discrete time model to get the same result. This shows the magnitude response of the digital filter. As another example, for the LTI system defined by the differential equation shown here, let's use the bilinear transformation to obtain the difference equation modeling the corresponding discrete time system, assuming that we have 0 initial conditions. To do this, we first find the transfer function of the system by applying the Laplace transform to the differential equation. Taking the Laplace transform of both sides of the equation and simplifying, we find the transfer function as the ratio of y of s over x of s. Defining the transfer function, we can plot the magnitude response of the system as shown here. Then we apply the bilinear transformation to get the discrete time transfer function. Using the coefficients in the transfer function, we write the difference equation as shown here. Let's find the unit sample response of the filter. Here you can see how the unit sample response of the discrete time filter changes over time. In this lesson, we use bilinear transformation for IIR filter design. We observe that the bilinear transformation maps a stable and causal analog filter into a stable and causal discrete time filter of the same order. We also went over the details of the design of a discrete time Butterworth filter.